Estimating surface area is probably one of the most daunting tasks for the new electroformer. Although it's true if you calculate the surface area exactly, you'll have the most consistent and accurate results. It's also true that if you estimate and you get kind of within the range of what the real surface area is, you'll still get very good results. And I want to emphasize that these very good results are still indicative of making an estimation. If you set the power supply to some random value or use the common misconception of low and slow, I can guarantee you will not get consistent results. You might get lucky and get some good results, but you will not get consistent results. But in this video, I don't want to go into the mathematics of anything. I still want to make this kind of a broad scope video. And so therefore, I'm going to give you some conceptual ideas of how to approach estimating surface area rather than calculating it directly. So to estimate the surface area of any complicated shape, like these Christmas tree branches or anything, we're first going to have to kind of start from the basics. Now, I will cheat and give you one singular equation for this whole video. Length times width. So that's the surface area of a rectangle or square. So the length on this square is 1 inch, and then the width is 1 inch. So 1 times 1 square inch. Now, for electroforming, if you've painted the backside, then that's also an additional square inch that you've painted. So this is actually 2 square inches. And then you can think about the surface area of this edge, but for something this thin and stuff, again, if we're estimating, then you can kind of say that this is a negligible amount of surface area. And so this is just 2 square inches. Now, where it gets fun is when you have things that aren't squares, like circles. Now, we know the surface area of this to be pi r squared, but I said that I wasn't going to use any more equations. So let's just say that we have no idea how to calculate the surface area of this circle. And this could not be a circle. This could be like any weird amorphous shape that you could think of, right? How do you calculate the surface area of that just using intuition? We use a tactic called a Riemann sum. Now, a Riemann sum may sound very complicated, but all it is just this methodology, this thought process of, I don't know how to calculate the surface area of this, but I do know how to calculate the surface area of this. I know this is 1 square inch. So I can just estimate this circle by tiling in this 1 square inch thing. Now you could use graph paper, or as you've seen here, I've tiled in 10 of these, and kind of the key to the Riemann sum is that you are really estimating it, like visually. So there's kind of this area that's not represented here by the 1 square inch tile, but you can kind of visually say, well, that's about that much of that. And then here, this area that's not represented might be a little bit more of that. And this area here is this area here, and so on and so forth. Like that kind of averages out that. And again, the whole idea of the Riemann sum is that you're just kind of getting this average surface area with something you do know the surface area of. And I've conveniently marked it to 10 square inches, and I'll have you know that I actually laser cut this to be exactly 10 square inches of surface area. So this goes to show that although it might not be exactly precise, you still get a pretty good estimate of what your surface area is just using a Riemann sum. The concept of the Riemann sum can be extended up from 2-dimensional things to 3-dimensional things. So if I were to try to estimate the surface area of this might be very complicated if I don't know how to calculate the surface area of all these little triangles of this dodecahedron kind of shape. Then I might just estimate it as a cube. I mean, this is kind of the same volume in a sense. And so, therefore, if I were to just calculate length and width of this cube face and then add all six sides of them, then that's probably going to be very close in surface area to this dodecahedron shape. And so, extending the concept of this Riemann sum thought process of just kind of estimating things by their most basic shape, you can extend this to even the most convoluted, complex shapes like this pine tree, where each one of these needles is just a little cylinder. And so you can calculate the surface area of a cylinder fairly straightforward using an online calculator, and then just kind of estimate how many of these cylinders there are, and you'll get a very close approximation to the total surface area of this structure.